Our chemistry, we're going to go on to a new subject. It's called limiting reactants. So how many cakes can you bake? So I'm going to give you some ingredients. To bake one cake, you need 1 cup of milk. To bake 10 cakes, you need 10 cups of milk. To bake one cake, you need 2 cups of sugar. 10 cakes, you need 10 times that much, 20 cups of sugar. To bake one cake, you need 5 cups of flour. To bake 10 cakes, you need 10 times that much, 50 cups of flour. One cake, 3 sticks of butter. 10 cakes, you need 30 sticks of butter. And to bake one cake, you need 6 eggs. To bake 10 cakes, you need 10 times that much, 60 eggs. So now I'm going to give you some ingredients, and you tell me how many cakes you can bake with this many ingredients. I'm going to give you 10 cups of milk, 20 cups of sugar, 50 cups of flour, 30 sticks of butter, and 6 eggs. So how many cakes can you bake? Well, you can see you have enough ingredients to make 10 cakes with everything except the eggs. And for the eggs, you only have enough eggs to make 1 cake. Therefore, you only have enough ingredients to make 1 cake. All the rest of the milk, sugar, flour, butter, you're going to have to just put back away. You can't use it. That's what a limiting reactant is in chemistry. It's the thing that you run out of, the reactant that you run out of first. And that's limiting the amount of the reaction that can take place. So the third column can produce only 1 cake because there are only enough eggs for 1 cake. All right, so let's do a problem here. Limiting reactants deals with the situations where one of the reactants is consumed, runs out before the other. In a limiting reactant problem, we want to be able to identify the limiting reactant, the excess reactant, that's the reactant that's not completely consumed, the amount of excess reactant remaining, the quantity of the products that can be produced. Okay, in the following combustion reaction, 2 moles of oxygen react with 1 mole of CH4. And you can see that in the chemical equation. 1 mole CH4 for every 2 moles of oxygen. But what if there is more or less than 2 moles of oxygen for every 1 mole of CH4? Then one of the reactants will run out before the other. The way to perform the excess reactant problem above is to run the reaction twice. So we're going to do it the first time when we use all of the CH4, that's completely consumed. The second time we're going to run it when all of the O2 is completely consumed. Okay, so here's an example. We have 6.42 grams of CH4 and 35.2 grams of O2, and they're reacted in a combustion reaction. We want to determine the 5 things below: the limiting reactant, the excess reactant, the amount of excess reactant, how much is left over, the number of moles of CO2, and the number of moles of H2O. So there's the question again, there's the situation. So first convert grams to moles. Remember, chemical equations only speak in moles. They don't understand grams. If you don't do that conversion, then you can't do this problem. Okay, so we're going to take the 6.42 grams of CH4, and then you compute the molar mass of CH4. There's 1 mole CH4 for every 16.05 grams of CH4, and you need grams of CH4 to cancel out, and you end up with moles of CH4, and that gives you 0.4 moles of CH4. Do the same thing with oxygen. We were given 35.2 grams of oxygen. The molar mass equivalency is 1 mole O2 equals 32 grams of O2, and if you turn that into a conversion where the grams of O2 cancel out, you end up with 1.1 moles of O2. Okay, so now we're going to run the reaction twice. Reaction 1 uses up all the 0.4 moles of CH4. Reaction 2 consumes all the 1.1 moles of O2. That's what we calculated we had. And we set 2 rows of boxes below the reactants to run each reaction. So in the first set of boxes is that's the reaction we're going to use all the CH4. In the second, we're going to use all of the moles of O2. So there we go, that's what we have. So Reaction 1 consumes all of the 0.4 moles of CH4. Okay, reaction 2, all of the moles of O2. So in the first box, below CH4, and in the row that says all CH4, we're going to place the number of moles, not grams, number of moles of CH4. And we see up above is 0.4. Next, we're going to say how much O2 must we have to react all 0.4 moles of CH4. And you can see it's a 2-to-1 relationship. That means we need twice as many moles of O2 to react all of the CH4. So 2 times 0.4 is 0.8. In order for this to react all the CH4, you have to have 0.8 moles of O2. Now we're going to go down below and we're going to see what it takes to consume or to react all of the O2. And it says up below that we have 1.1 moles of O2. So there we put that in the row that uses all the O2, that's all we have, and in the column that says O2. So then we have to work backwards and figure out how many moles of CH4 do we need, and it's going to be half as much. So we're going to go ahead and put that there. So half of 1.10 is 0.55. So when you're done with this, you notice that all the ratios are 2-to-1. In the chemical equation, it's 2 moles of O2, 1 mole of CH4. In the first row below, it's 0.8 to 0.4. That's a 2-to-1 ratio. And in the bottom row, it's 1.1 to 0.55. There's always twice as much O2 as CH4. So now we're going to see which of these reactions can run. Okay? So you got to ask yourself, do we have at least this many moles to work with? What that means is, at least means you have that many moles or more. That many moles or more, okay? So let's look at the CH4, the first one. Yes, we do have 0.4 moles of CH4. That's exactly how much we calculated we have. So yes, we have that. Do we have 0.8 moles of O2? And you look, yes, we do. We actually have more than that. We have 1.1 moles of O2. So yes for that one. Now we go down below. Do we have 1.1 moles of O2? And the answer is yes. That's exactly how much O2 we have. Now we go back to the box on the bottom left. Do we have 0.55 moles of CH4? And the answer is no. We only have 0.4 moles of CH4. So the limiting reactant is the column with the no in it. It's the CH4 column that has the no in it. So CH4 is the limiting reactant. It's the one that's going to run out first. The excess reactant is the other one. It's the O2. That means we have more O2 than we need. But how much more? Well, the reaction that's going to actually run is the one up above with the 2 yeses in it. The 0.4 moles, 0.8 moles reaction. Use all the CH4. That means we're going to need to use 0.8 moles of O2, 0.8 moles of O2, but we were given 1.1. So if you do a simple subtraction, 1.1 minus 0.8, that means you're going to have an excess of 0.3 moles of O2. And you see that down below in the blue box. So the excess reactant is the blue column with 2 yeses in it. So in that column you have 2 yeses. The row in green now that you see that just appeared is a reaction that can run completely. In other words, it's the row that has 2 yeses in it. 0.40 is yes, 0.80 is yes. So that's the reaction that can actually run. Okay, the row down below will not run to completion. You have 1.10 moles of O2, but you're going to run out of CH4 before you run out of O2. So that means the CH4 is limiting, and that reaction will not run to completion. You will not be able to use the 1.1 moles of O2. Okay, so now we're going to run 2 reactions, and this is the reaction that will run, the one that has the 2 yeses in the row with 2 yeses. And the reaction will run because there are at least 0.4 moles of CH4 and at least 0.8 moles of O2. That reaction down below will not run for the reason I gave earlier. So the row with 2 yes in it is the reaction that will run. This is a reaction in the green box. Okay, now we can compute the number of moles of CO2 and H2O that can be produced. So from the reaction, the equation tells us that we will produce the same number of moles of CO2 as moles of CH4. Why? Because they have the same coefficient in front of them, a 1 and a 1. That means since we actually used 0.4 moles of CH4, we can produce 0.4 moles of CO2. Now, how about H2O? Well, you see H2O has a coefficient of 2 in front of it, and so does O2. So however many moles we have of O2, we're going to be able to produce that same number of moles of H2O. And so that's going to be 0.8 moles of H2O. Using molar mass conversions, we can compute the grams of CO2 and H2O if we wish, but we won't do that in this problem. Okay, now we're going to move on to a different topic, theoretical yield. The theoretical yield of products in a chemical reaction is the amount that the chemical reaction says you should get. In other words, when you do the stoichiometry that we've been doing, that's how much you should get. But in the real world, you don't always get that amount for a variety of reasons. So the actual yield is how much you actually get in the lab. So actual yield can differ from theoretical yield for several reasons: human error in measurement, materials lost remaining in the container, or spillage, or evaporation. Okay, so the difference between the actual and theoretical yield is measured by percent yield. And here's the formula. The percent yield equals the actual yield, what you got in the lab, divided by the theoretical yield, what your chemical equation stoichiometry said you should have gotten, and then you multiply that by 100%. Okay, so let's look at this. Compute the theoretical yield and percent yield for grams of water for the following balanced reaction if 6.5 grams of CH4 is combusted in excess oxygen. The actual yield in the lab was 12.09 grams. I'm just giving that to you, okay? So we start with 6.5 grams of CH4. We do our molar mass conversion. We get moles of CH4. Now we move across, we get 0.8 moles of H2O, and then use the molar mass of H2O to come back out and get the grams of H2O. So there's the way you would write it in the equation. It's a 3 conversion equation because you have 3 arrows, so you practice those. So that means the equation says you should get 14.4 grams of H2O. The percent yield is computed as follows. So you're going to take the 12.9 grams of H2O that you actually got in the lab, divide it by what the chemical equation told you should have gotten, 14.4 grams, multiplied by 100%, and you get 84%. So you got 84% as much of the product as you thought you should get based on the equation. All right, and that takes care of this lesson on limiting reactants and also on theoretical yield.